Today we're going to continue looking at interpreting definite integrals and what they mean in context. One way we can interpret the definite integral is to look at the units of the function f of x and the units of dx, the function that we're integrating, and the units of the variable. The units of the definite integral are going to be whatever units we have for f of x multiplied by the units of x. This goes back to thinking of integration as multiplication, but one of the factors is variable. We're just multiplying values of the function by some small change in x. So whatever units are attached to the function, we multiply those by the units of the dx, which will be the same as the units of x. So for example, if our function is measuring miles per hour, and we integrate with respect to hours, we take miles per hour and multiply by hours to end up with miles. So the definite integral will be a change in distance. If our function is density, grams per cubic centimeter, and we integrate with respect to volume in centimeters, then a definite integral will represent the change in mass, or the change in mass in grams. If our function, so in both of these cases, something is canceling out. So if I have grams per cubic centimeter and multiply by cubic centimeters, we'll end up with grams. We don't necessarily have to have something canceling out for the units of our definite integral. Work is equal to force multiplied by distance. So if our force is being measured in pounds and our distance is being measured in feet, then the units of the definite integral will be pound feet. So whatever f of x is multiplied by whatever units of f of x multiplied by the units of x will give you the units of the definite integral. This is always going to be a change as x changes on the interval as x goes from a to b. So a and b will have the same units as the dx. So back to our example with speed and time. If f of x is in miles per hour and dx is being measured in hours, a and b are both times in x. So the definite integral from time a to time b is going to be the change in distance in miles. So it's how much the distance has changed from time A to time B. Any questions? Right, let's look at an example where instead of finding an antiderivative, we have the function that we're integrating is just going to be listed as a table. So I'm going to establish a function. Let's let E of E be the emissions of nitrogen oxides. I'm stealing this one. So let's let E of T is the emissions of nitrogen oxides and this is going to be in, in millions of metric tons per year. So here are the units of E of T. And this is going to be at T years since 1970. So our function T is going to be measured in years. So we should see what's going on right now. The units of E of T, the units of our function, is going to be millions of metric tons per year, and we're going to multiply that by the units of T, which are years. So the years are going to cancel out, and so we'll have emissions of nitrogen oxides, or the total amount of nitrogen oxides emitted in millions of metric tons, because the years will cancel out. This is a very common phrasing that we want to point out. So this is at t years after 1970. So what this means is that t equals 0 corresponds to 1970. And t equals 1 will be 1971, and so on. It's not useful to look at the emissions of nitrogen oxides at year 0, because I don't think we have that information. But we do have that information for 1970, when we actually started thinking, hey, maybe all this burning stuff isn't such a good idea. And of course, as a group, we still aren't convinced of that, because good job, humans. So now, instead of giving you a function to actually work with, I'm going to give you a table of values. So let's say the year 1970, the emissions in millions of metric tons per year was 26.5 million metric tons per year. Remember, this is a rate that we're going to be, this function down here is a rate. 1975, 26.2. In 1980, 27.1. In 85, we got 25.7. 1990, 25.3. That'll give us 20 years of data. All right. So let's suppose that we wanted to integrate this function e of t dt from 0 to 20. First of all, we should point out that this 1970 corresponds to t equals 0. Here's t equals 5, t equals 10, t equals 15, and t equals 20. What we're going to do is assume that e is constant for each of these intervals. So we're going to calculate the definite integral by assuming that e is constant on each of those intervals. First of all, let's talk about the units. Let's see what the integral from 0 to 20 of e of t dt means in this situation. So the E of t is going to be emissions of nitrogen oxides in millions of metric tons per year. Millions of metric tons per year. In this case, t is measuring time in years. So the units of dt are time in years. And we're going from t equals 0 to t equals 20. So from 1970 to 1990. So from 1970 to 1990, we'll have the millions of metric tons. And that's it, because the years cancel. So the years cancel. The units of the definite integral will be the units of the function times the units of t. So the years cancel. And so the units of this are millions of metric tons. The 0 to 20 means from 1970 to 1990. So we'll end up with the millions of metric tons. It'll be the change in nitrogen oxides. Let's say the net change in the amount of nitrogen oxides between 1970 and 1990. It'll be the net change in the amount of nitrogen oxides, in millions of metric tons from 1970 to 1990. When we're interpreting a definite integral, we could always lead with net change. Then what are we describing? So the emissions was the rate of change of nitrogen oxides because it's millions of metric tons per year. So we'll just have millions of metric tons per year times years. So the years cancel and we get millions of metric tons. The 0 to 20 means from 1970 to 1990. Any questions? So next, we want to actually estimate this value by assuming that the function is constant for some intervals. So let's do that. So let's estimate the integral from 0 to 20 of e of t dt. Oops. Remember our strategy for estimating a definite integral. We assume that e of t is constant for changes, small changes in t. In this case, the smallest change in t we can get is 5 because we don't have any other information. So we're going to assume e of t is constant for small changes in t. Small changes in t is going to be a delta t. Because we have the information is listed in a table, the smallest change in t we have is 5. I do not have a value for e of 1. I only have data every 5 years, so the smallest delta t that I can use is 5. So one way we can do this is with the left-hand value. I can take this first rectangle, and I can either use the 26.5 or the 26.2. The 26.5 is going to be the left endpoint, and then the 26.2 will be the right endpoint for that first rectangle. So here are all the rectangles that we're going to use. There's a delta t of 5. Here's another delta t of 5. A third delta t of 5. And there's our fourth delta t of 5. So we are doing this with n equals 4 rectangles. We're going to be calculating the area of these 4 rectangles. The area of each rectangle will either use the left endpoint or the right endpoint for the height. Let's start by using the left endpoint for the height. So this first rectangle has a left endpoint of 26.5 and a delta t of 5. So we're estimating the integral from 0 to 20 of e of t dt. We're going to take the 26.5 and multiply that by 5. This second interval from 5 to 10, we'll use the left endpoint, which is 26.2, times the width, 5. This third rectangle, we'll use the left endpoint for the height, so 27.1, times the width, 5. This fourth rectangle will have the height of 25.7 times the width, 5. I want to use multiplication to multiply the length times the width, but the length is variable. So I assume that the length is constant for small changes in the width, so that I can use multiplication, and then I just add up the 4 areas. Here I use the left endpoint for the height of each of those rectangles. So I'll just need a 26.5 plus 26.2 plus 27.1 plus 25.7, all multiplied by 5. I can factor it out because they're all being multiplied by a delta t of 5. So our total here is 527.5. And this is going to be in millions of metric tons. Of nitrogen oxides. Any questions? It is very important that you look at this as the areas of 4 rectangles. If you're wondering, what about the 25.3? You need to step back and look at this as the areas of 4 rectangles. 1 rectangle, 2 rectangle, 3 rectangle, 4 rectangle. And I use the left endpoint for the height of each of those 4 rectangles. Now that's not the only option. That's assuming that for the first 5 years, it was 26.5 the whole time. But maybe immediately after it was 26.5, it dropped down to 26.2 and it was a 26.2 for 1970 to 1975. So let's use the right endpoint for the height. Let's use the right endpoint for the height. I still want to calculate the integral from 0 to 20 of e of t dt. But now for this, oops, I need this back. For this first rectangle from 0 to 5, I'm going to use the right endpoint, 26.2. And I'll multiply that by the width. Then for this second rectangle, instead of 26.2, I'm going to go to the right endpoint and say it was 27.1 the whole time. And I'll multiply that for those 5 years. Then for this third rectangle, I'll go to the right endpoint and say it was 25.7 the whole time. And then I'll go to this last rectangle and I'll use 25.3 for that last 5 years that we're considering. Once again, we're assuming that the function is constant for these small changes in t, so that we can multiply. So in this case, I'll have 26.2 27.1, 25.7, and 25.3, all times 5. So 521.5. And this is still millions of metric tons. So in those 20 years, at these rates, we're estimating somewhere between 521.5 million metric tons and 527.5 millions of metric tons of nitrogen oxides. Any questions? Once again, our assumption is that our assumption is that the function is constant on each 5-year interval. So remember, our assumption we assume that E of t was constant on each 5-year interval. Once something is constant, we get to use multiplication. Any questions? Great. Now, since we have two, one high and one low, we might be tempted to find the average of these two. But until you can tell me what assumption we would be making when we make the average of these two numbers, then I don't want you finding the average of these two numbers. Because this whole thing where we're like, oh, we've got one here, one at one end and one at the other end, let's just average the two, has got to stop. It's a very bad habit that we've gotten into as humans. We'll just average things. But we don't even know what that means in this case. So until you can draw me a picture of what's going on in that average, you don't get to average them. You kind of have to for this particular homework problem. So you're going to have to work that out. Any questions? So before you go and just average the numbers and just blindly average the numbers like some robot, tell me what that assumption means. If we average these numbers, what is our baseline assumption? If we average the numbers, then what is it that we are assuming?
Isn't it basically that every 5 years, 524.5 million metric tons of nitrogen, blah, 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 go out in the atmosphere?
No, this is not, that wouldn't be every 5 years. That would be the conclusion that we draw. What assumption are we making when we say we'll just average the two? We begin at these two values by assuming that the function was constant on each 5-year interval. What changes if we find the average between the two? Because then we would not be assuming that the function is constant on each 5-year interval. So that's what needs to change, not the conclusion that we would draw. Because based on this left-hand estimate, we're saying from 1970 to 1990, there were 527.5 million metric tons emitted of nitrogen oxides emitted. in this in this calculation, we would come to the conclusion that from 1970 to 1990, 521.5 million metric tons of nitrogen oxides were emitted. If we assume that it's exactly in between, that's still based on the conclusion that from 1970 to 1990, 524.5 million metric tons of nitrogen oxides were emitted. So it's not what conclusion we would base. It's what are we assuming that's different than assuming that the function is constant on each interval. Are we calculating, are we still doing the same thing where we're finding the area of a bunch of rectangles and adding up the areas of those rectangles? The answer is no, we're not making that assumption. What assumption are we making? That's what I want to know. It's not about the conclusion, it's about the assumption that we make to arrive at that conclusion. Any questions? What about trapezoids? Let's pause the video here and think about that.